Alright, so in this part, we're doing section 7.3, trigonometric substitution. So this is kind of a different topic than the last one, where you're getting the higher powers of trig. This one's going to be a little different because we're actually be doing a substitution rule. Instead of a u, we're going to be using theta instead, and then going back to x. And it's going to be a little bit more complicated when it comes to it. We have to do one extra step because now we're doing theta instead of x and just instead of u, okay, when it comes to it. So a brief little reminder when it comes to right triangles and the trig functions themselves. So given a right triangle, where say this is theta, okay? So if this is x, this is a, so therefore according to Pythagorean's theorem, this is x squared plus a squared, right, when it comes to it. And the trig functions we're going to be dealing with in this section more precisely is just going to be roughly 3 of them. So this is cosine theta, and if you guys remember, that is adjacent over hypotenuse, so we just x over the square root of x squared plus a squared. Sine theta was just opposite over hypotenuse, so this is going to be a over the hypotenuse. And then finally, tangent theta is opposite over adjacent. In other words, a over x in this case. Okay? And these are the main 3 we're going to be dealing with in this section, how to use those substitution methods when it comes to it. Okay? With a little bit of secant involved, but again, secant's not too difficult because secant theta is just the opposite of cosine, right? Because they're inverses, so it's just this on top over x. And same thing when it comes to cotangent and cosecant, right, when it comes to it. Okay, but the main focus is we're going to be using this triangle to actually find these integrations of these portions. Okay, and the first way we're going to do it is, again, just like the last section, is a couple of properties when it comes to it. Okay, so the main properties we're going to do, or the main techniques we're going to be dealing with, is, well, using these expressions when it comes to integration. Okay, so if we have the expression of the square root of a squared minus x squared, so in other words, over here we have that situation. Instead of plus a squared, it's just minus the opposite sign. So therefore, we're going to be using x equaling a times sine theta as our substitution. Notice now it's in terms of theta. Okay, so we're just going to plug this whole thing in for x and just slowly simplify as best we can. And eventually, we're going to be using this property to equal cosine theta. And again, eventually at the end of that, it all simplifies actually pretty nicely when it comes to it. But again, the whole process is just making that portion when it comes to it. Okay. And if we have the opposite, if it's a squared plus x squared, or x squared plus a squared, because it doesn't matter because it's addition, we're going to be using tangent instead, so a times tangent. And then we're going to be using the property of the Pythagorean one when it comes to it, of secant squared equals 1 plus tangent squared. Okay. And the last scenario is flipping these, right? So if it's x squared minus a squared, we'll be using x is equal to a times the secant theta. And using our substitution again, same as the Pythagorean identity we did above, right? Just in terms of tangent this time. Okay. Now again, the most difficult part of about this section is the setup. When it comes to it, it's going to be really, really messy, but it's actually going to be broken. The integral itself will be really, really nice. So that's the whole point of this, is just somehow manipulate this in such a way, therefore it's an easier integral to actually look at and evaluate when it comes to it. Okay, so let's just look at an example, so how we would go about doing this process. Okay, so first example is right here. So we want to find the integral of 1 over the square root of x squared plus 25. Okay, so right off the bat, if you noticed, right, this is kind of the situation we have in part B. Right? The only difference is just x squared is here and a squared there. So essentially, part B can be written as this way as well. Okay. So therefore, we know a in this case is going to be 5 because it has to be a squared. So the only way to get 25 is when you square it is 5 squared, right? So that would portion. So using this template, we're just going to follow this along. So therefore, I'm going to let x to equal 5 tangent theta. So therefore, the derivative, the derivative is going to be 5, and the derivative of tangent is secant squared theta. So now plugging everything we know, so plugging in x for here, and dx equaling that instead. Oh, and this is going to be, sorry, d theta. So plugging all this into here. Again, it's going to look like a horrible mess, but it's actually simplified kind of nicely. So the 1 and the dx is now going to be replaced with that. So it'll be 5 secant squared theta d theta. And on the bottom, it's going to be 5 10 theta squared plus 25, like that. Okay. So if we square that, we get 25 10 squared theta plus 25. Okay. Now if you factor out a 25 from the bottom, we get 25 and then tangent squared plus 1, right, d theta. Okay. Now notice, this is the reason why we use this substitution. That's exactly what we have. So instead of tan squared plus 1, we can now replace it with secant theta instead. And now this square root actually goes away, right? Because the square root of 25 is going to be 5, and the square root of secant squared is just going to be secant. So even better. So now all this actually will cancel out. Well, a lot of this will actually cancel out. And look at that. So the 5's cancel, and one of the secants cancel. So really, this is now just the integral of secant theta. So notice the setup was the difficult part. Now the integral is actually much easier to deal with, and we know the integral of this is just going to be the natural log of secant theta plus tan theta plus c. Okay. Unfortunately, however, we're actually not done, because over here, right, it was in terms of x, but now we have in terms of theta. Okay. So this is where the triangle comes into play here. Okay? So going back, we're going to make our new triangle for this question. And how we're going to make this triangle is from the very beginning how we applied x. So if I just solve for tangent, this is going to be x over 5 is equal to tangent. And we know tangent is opposite over adjacent. So in this case, x is the opposite, 5 is the adjacent, and here we have x squared plus 25 as the hypotenuse. And then from there, now we're going to plug in each one individually. So our last step is right what we have. So this is going to be the natural log of secant theta, which is hypotenuse over adjacent. So it's going to be the square root of 25 plus x squared over 5. Oh, sorry, over 5. Okay. Plus tangent theta. So we already talked about tan theta. Tan theta is just opposite over hypotenuse, so that's just going to be x over 5 plus c. And there is our integral. Voila. All that work just for that integral there, right? So that's how we're going to do these processes. It will take a little lengthy to get there, but the integral itself won't be that hard. Setup is the most difficult part. So let's try another example. So let's find the integral of 1 over x squared times the square root of x squared plus 64. Now, let's just get, if that wasn't there, notice we have the same situation as above, meaning we're almost identically going to copy what we just did on the above example because we have the same situation happening. In this case, a is going to be 8, right, because 8 squared gives you 64.